Hello, hello. Testing, hello, hello. Can we start settling down there at the back, please? All right, good afternoon, everyone. I'm going to give it another minute for people to start trickling in, and then we'll start at 2 minutes past 1. Thank you. Okay, it's now 2 minutes past 1, and I think I'm going to get started because we have a very, very long lecture to take you all through. I was chatting to the team this morning, and well, over the past few weeks, given the talks we've seen this week, it's very difficult for us to explain what we do without getting technical. So just bear with us. We're going to try to take you through what we do in the Digital Signal Processing Group. So good afternoon, everyone. Welcome to day 4 of Engineering Week Plus. I only found out yesterday what the plus actually meant, so you're not the only one who ever asked that question. For those of you who don't know me, I'm Tyrone van Balla. I'm the functional manager for the Digital Signal Processing Group. And yeah, this is what we do. So first of all, what do we do in the DSP group? Well, our mission is to deliver leading world-class digital signal and data processing systems to support and enable radio astronomy in Africa and beyond, and to contribute to the advancement of the field. Our team has quite a broad and diverse range of competencies, all the way from data processing, which includes digital signal processing, as well as science data processing as well. Pipelines, so how do we put these different processing blocks together to form pipelines for DSP, for radio astronomy, real-time DSP, I might add, and also near real-time science data processing for the formation of images. And then looking toward the future, we're looking at combined pipelines for both DSP and science processing. That all makes sense once you see the rest of the presentation. Because of the data rates and the volume of data that our team is meant to process, a large part of what we do is acceleration of algorithms. So our team is quite skilled and competent in acceleration on both GPUs, so graphics processing units, as well as traditional, or in radio astronomy, traditional FPGA or field programmable gate array accelerators. Again, because of high data rates, we also quite experienced in high-speed data transfer. Most of you know about the 40 gig network that we have on Meerkat. So our team is skilled at building terabit scale data networks and also optimize. Sorry, is there a question? Or maybe if you can mute, please. Optimizing off-the-shelf hardware for high throughput ingest and egress. So we try and get all the performance we can out of your off-the-shelf network cards and other networking equipment. And then also, last but not least, we have hardware and FPGA development. So again, our team is quite skilled in low-level FPGA hardware development, and that allows us to look at custom hardware-accelerated applications for the signal chain. Then there's also some auxiliary and support competencies in our group. So qualification, continuous integration, and continuous delivery, as well as operational support for the systems that we build. And then governing all of this is team functional and technical management. So who makes up the DSP group? So I've kind of tried to break it up to show, because we do a lot of things. I'm not going to go through names. The faces should be recognizable to most of you. I've tried to be fair, and I've chose the least glamorous pictures for everybody. So yeah, so we basically consist of the Meerkat Extension Correlator Development Group. They build in the Meerkat Extension Correlator, the Meerkat and Meerkat Extension Pipelines Development Team that does the SDP pipelines for Meerkat and Meerkat Extension. We have a newly formed Smart NIC prototype team. They're looking at building custom Smart NICs that you'll hear about at the end. We also have what we call a DSP research group, a group that's focused on doing exploratory or computational DSP research to look at how we can optimize and do better at our signal processing. And then last, but certainly not least, we have ALEC. That is the Meerkat correlator support. Most of you have probably interacted with ALEC, whether you are new or old at Sereo. All right, so now what do we do? So to explain what we do, unfortunately, we need to understand the basics of radio interferometry. So I'm going to give you a very simplified crash course in what it is that we actually do for radio interferometry, and you'll see how that relates to what our team does. So basically, I'm not going to point, the picture should be, I guess I'll point for the benefit of people that are in the audience. Basically, we are observing these celestial bodies in outer space. And all of these bodies emit some sort of radio signals. And we've heard about RFI in the beginning of the week, and receivers as well. And we've got a dish that basically then receives those signals. And the whole point of radio astronomy is to learn about the structure or positional structure and characteristics of these bodies in outer space. And what the scientists do is they take that data, lots of processing, and ultimately turn it into a nice image. So that's basically what we do. We make nice, pretty images of the universe that we can't see with our eyes. So as you're probably aware, most of you know about photography and have used cameras before. If you want nicer, better, cleaner images, you need more resolution. So in photography or optical photography, I guess you need a bigger lens to be able to capture more light, and that's how you get a better image. In radio astronomy, if you want more resolution, there's really two ways that you can achieve this. So one is build the biggest dish that you can. And obviously that has been done in various instruments, but it starts to exceed, or near the edges of what's actually practical and achievable, mechanically and otherwise. It's also very expensive to build a single large dish. What you could also do is, build an interferometer, which is basically building, multiple smaller little, let's call them telescopes or dishes, and sort of synthesizing them using signal processing techniques to get them to act as a single large telescope. And the difference between the two cases is in single dish radio telescopes, your resolution is proportional to your diameter of your single dish, whereas in an interferometer, the resolution is proportional to the length of the baselines, and that's just the distance between the dishes in your array. So interferometry, yeah, this is just a comic in case people wanted to laugh at this point, but it kind of just explains, the high-level concept of interferometry. So if you space two small dogs by some distance d, they behave as a single big dog, and that's basically radio interferometry. That's all you need to know about it. Unfortunately, it's a little bit more complicated for us. So let's look at a very simple case where we're observing, let's call it a single source or one signal coming from a source. If we have two dishes that are spaced apart, these are the radio waves coming through, or representation of them. You can kind of see, hopefully from this graphic, that it's going to reach the two dishes at different times, and there's a little bit of a delay between them. So we call that delay tau. Now, with our digital backend systems, we can actually calculate and compensate for that delay. It gets more interesting when we have multiple sources, or we have multiple signals that we're getting from the same source. So if there's some interesting physical characteristics to the source, we'll get a few different signals, emanating from it. In this case, we have then two delays that we measure. And again, our digital backend systems allow us to measure and compensate for these delays. And really, it's those sorts of delays that tell us interesting things about what it is that we are observing. So finally, where do we actually fit in as the DSP group? Well, this is kind of a, again, high-level representation of the Meerkat signal chain, all the way from dish, the digitizer, the receiver, the fiber networks, all the way through to the KAPB. And really, this little black or red box in this case captures what our team does. So we are responsible for the end-to-end data processing pipeline from raw data, raw digitizer data, right through to image. So the correlator is the bit of the system that would work out and compensate for those delays I mentioned. And then the science processing pipeline would actually take those visibilities that we produce and turn them into radio images. So to start off, not yet, quickly, project involvement. So I'm just going to end off on this slide. We are involved in a number of projects at Sereo. So Meerkat and Meerkat Extension, most of you know about. We build the correlator beamformer for both projects, the science data processing pipelines, and also the high-speed data network. On AVN, we've built the single dish backend system. And then we also have a couple of R&D projects, the SmartNIC that I mentioned. We are involved with the Hartrau spectrometer upgrade, as well as a Hartrau VLBI correlator. And then there's some computational DSP. And then for SKA MID, some of us, and again, not to single out Alec, Alec is involved in some of the correlator acceptance and integration verification activities. All right, so yeah, that's it from me. I hope you enjoy the rest of this talk. First up is Andrew and James, and they'll be talking to you or taking you through correlators and data transport.
Right, thanks, Tyrone. So Tyrone gave a fantastic introduction there, made my life a lot easier. And what I'm going to now do is lift the lid on what he's got showing up here to show you a little bit, a sneak peek of what's actually underneath the hood and how we actually do all of this from a relatively high level DSP perspective. Right, so looking at this in a very high 40,000 foot view kind of way, we have currently 64 antennas on site, and each of the receivers on those antennas are basically converting electromagnetic radiation, what's being received, into raw voltages. Those voltages are digitized, or those signals are digitized and then sent through a network, which we'll discuss shortly, into what we call our F engine. And this is the first entry point to the overall correlator. What it's essentially doing is just doing the process of channelization. We'll go a little bit into that shortly. But it's effectively taking this signal, breaking it up into various frequency components, which indicate what it is present within that signal, and then sending it off to what we call the correlator, well, which is actually an X engine. So this is conceptually what's actually happening. And each dish has got its own individual channelizer, but all of that data gets brought together in the correlator to produce the product, which we're calling visibilities. Taking a slightly deeper dive into the actual F engine, just looking at it from a single antenna perspective, but it carries for each one of them, is we push it through what's called a channelizer. Now it's simply represented by a single block here. You'll see the finer details of it shortly. But in essence, what we're doing is we're taking the signal, an analog signal at that. What's happening up in the front end is, if in this particular case, we look at L-band, we're digitizing an 856 megahertz bit of bandwidth, and then we literally split it into chunks, to hold the analogy really, in the frequency domain. And we want to see what is relevant within each particular frequency component of that particular signal. That then gets sent further down the line for further processing. But I have to first just deviate at this point and say, you may have heard of a few terms. There are actually two variants of our F engine. We do what's called wideband and narrowband. And this slide just depicts the difference between the two of them. Sorry, the coloring is not so great here, but effectively we have in the wideband case, we have an 856 megahertz bandwidth that gets digitized and channelized. And in narrowband, it's the same 856 megahertz. The only difference is we take a chunk of it, 107 megahertz or 54 megahertz of it, and that can be positioned anywhere within that 856 megahertz band. And that then gets further processed. The other difference between the two of them, in wideband, we have got three flavors that you can work with, being a 1024 channel version, a 4096 channel version, or a 32768 channel version. In narrowband, there's only the 32K version of it. And whether you digitize in 53.5 megahertz or 107 megahertz, it doesn't matter. Taking an even gorier look at our F engine, Tyrone mentioned a few things like delay compensation. I'm not going to spend too much time on this slide, but this is just to show that there's a lot that happens under the hood. It's not just a simple case of taking some data, pushing it through an FFT, and you've got your result. There's quite a lot that happens, from unpacking, from timestamping, delay corrections, both in time and frequency domain, equalization, and of course the channelization itself. But all of that now gets sent one step further down the line into our correlator. Now, this again is at a very high level view. As you can appreciate, there's more than one dish on site. There's 64 of them. And I don't know, somebody can just mute themselves. The problem is scaled roughly by the square of the amount of antennas. And effectively what you're doing is you're taking one antenna and you have to compute or multiply its products with every other antenna. So as you can appreciate, as the number of antennas go up, so does the problem space. But at its heart, it's very simple. You're taking the spectra that's produced by one antenna and you're cross-multiplying it with another, and you're doing this in frequency domain as the process of correlation. And this produces an intermediate product, which is what science processing cares about, and Kim will talk about that in greater detail. Conceptually, how we actually do this, Omer originally referred to SCARA boards that we use on site. This does our processing, and it's not just one board that does this. We have to split this problem out across many boards. It's just the amount of data rate, the data that we're talking about, the rate of it, and the amount of processing that's required is not possible on a single device. So this gets split out amongst many, and how we do this is we take sections of the channelized data and we send them off to the various X engines that have been given the particular task. So all of the data from one particular section of the band from all antennas goes to one particular X engine core, and then another X engine core gets another section of the band. So they're getting data from every single antenna to be able to do the cross multiplication, and then this gets brought together. There's one extra section to it, which I'm not going to go into any great length at all, but there's what we call a B engine, which is beamforming. That is if you want to, instead of using 64 dishes independently, you want to create beams, or basically a larger antenna out of some of them, and you want to steer that beam. So we do have logic that's in place to do that as well. That's also happens in frequency domain, but that's a different animal in itself. So how is this all linked together? We've seen some top-level views of where we have the dish and the D engine. Heno and CS talked about that earlier in the week. This thing gets stitched together in a 40 gigabit Ethernet network, and we have these various processing levels of F engines, both the wide and narrow band, and our X engines, and the data is flowing between them. I'm now going to hand over to James, who's going to take you through the Ethernet network side of things. And then I will resume with the FPGA side of stuff.
Okay, thanks, Andrew. You're making me feel weird. I feel like I need to tell jokes or something. Okay, so the point that Andrew made previously is that all of these individual bits and pieces need to talk to each other somehow. There's a lot of computation that's going on here, and it can't all happen on one platform, on one box. And so he's nicely labeled it there as Ethernet. And that is what we do. So this is what we don't do. Image credit to the European Space Agency here. This is a tiny zoomed in photo from ALMA's correlator, ALMA in South America. And you can see there that these are individual custom little boards, and they've got Xilinx circuits on them, very similar to the ones that we use in our Scarabs. But the approach that they've taken to getting the boards to talk to each other is to make a big backplane. So this is a big circuit board with sockets that you plug the individual processing boards in. And then, so this has some advantages. It means you have very, very fine-grained control of what you want to do. The disadvantage is that it's a lot of work to do that. It's not really something that you can go to Incredible Connection and just buy off the shelf. And if there's something goes wrong, well, or if you decide you want to expand or upgrade it, then that's harder. This is what we do. We use just Ethernet. It is a little bit faster and a little bit more expensive than the kind that you plug into your fiber router at home, unless you've got a very, very nice fiber router. In which case, I want to know who your provider is. So this is a photo of admittedly now this photo is several years old, and those who have been in the KDRA will know why. But this is in rack B1. So these are each individual off-the-shelf switches. It's just bog standard Ethernet. These orange cables that are in there at the moment are connecting to other parts of the network, and these are our fiber transceivers that are just waiting to have the patch leads in them. These are the ones that are going to be connected. Well, they are connected at the moment, but when the photo is taken, they're going to be connecting the actual receptors to the data network. This is a diagram put together by Jason, who was Tyrant's predecessor, and in a sense my predecessor as well, because he was previously responsible for putting the network together. And it uses an architecture designed at Bell Labs by an engineer named Charles Claus. If you're interested in a bit of a history lesson, it has a sort of a two-layer thing. There are leaf switches which connect to your actual processing nodes, or your items that need to access the network, and then there are spine switches which connect to the leaves to join them all together to provide connectivity for them. And the reason that we use this architecture is that it makes it possible for any two of these nodes on the network to talk to each other at full speed with no blockages, because there is enough bandwidth. So for example, if you've got someone here on L30 that wants to talk to someone here on L26, but there's two sets of these things, then they can both run at full speed with no contention for the bandwidth. Yeah, there are some nitty-gritty details, but this is essentially off the shelf. Granted, it's the very expensive shelf, the one that they keep out of reach of children. But it's something that we don't have to develop in-house. We can just buy it, and that saves a lot of engineering time and lets us do the things that we want to do. Ludwig.
How is the leaf and the spine? Sorry. How is the leaves and the spines? How are they connected? Is it all the leaves to all the spines, or?
Yes.
Okay.
Yeah, that's a good question. So I'm going the wrong direction. Yeah, so every leaf has a connection to every single spine. And that, if you go down into the sort of theory of it, so we've got a bit of a system here. These are, you'll see that the spine connections are precisely half of the number of ports on each leaf. So that gives, when you have full bandwidth in, you can have full bandwidth going out as well. So with a 40 gig network, we have 18 spines. And so each leaf can connect 18 nodes. We only really use 16 of them, so we just have a little bit of extra redundancy, and just because that's a convenient number of scarabs that fit in a rack as well. So yeah, but that's a good question. Okay, then back to Andrew. Yeah. Ruford.
I remember back in the day when we had the 16 release, dish release, there was a lot of issues with the networks. It was almost like we were running them at like full capacity, and then you want to describe a couple of those?
So what you're talking about here is a little bit before my time. So I'm gonna pass the buck on that one and blame Jason. Yes, so there were issues. And we drive these links hard. So to give you an idea, the network is specified for 40 gigabit per second, and we're getting very, very close to that, 95 to 98% of the link utilization. And that can be quite challenging for even relatively modern hardware to cope with. So there was a bit of a process to get the design and the configuration stable. And to Mellanox's credit, they worked closely with us until we've got a situation, and Alec can either confirm or deny this. Yeah. 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 So they have worked with us pretty well to resolve those issues. Yeah.
Good, thanks.
Right, thanks, James. I'm now going to hone in a little bit more on the practicality side of it. He's talked about how we connect these things together. This slide depicts not only that, but also the sort of rates that we're talking about. If you look at, if you consider it's represented as a single switch in this particular diagram, but it's more than just that, as James has just shown. You have your fiber links from your dishes that are coming in. That's those rates are in the order of about 34 gigabits per second per antenna. So if you think your fiber at home is something impressive, go to site. And then that gets sent off, the data that gets ingested by the switch from the D engines gets sent off to the first port of call, which is an F engine. And now you'll notice that it's the same hardware for both F and X, and that's because we use the same hardware for both F and X engines. We just configure them differently. But I'll describe that shortly. Then the rates drop a little bit after some of that processing, and then eventually it lands up in some servers, which are SDP pipelines, and they then work their magic with creating the images from the intermediate products that we produce. Now, Omar did me a great favor early in the week when he introduced the Scarab boards and the Roach boards, and he talked about FPGAs, but he didn't really tell you what an FPGA is. So this is a single slide I'm gonna try and use to depict this. So for those who are well versed in this domain, please forgive the oversimplification. But essentially an FPGA is a silicon device that we can configure to do whatever we want really within the realm, within certain bounds of possibilities. Now there is the analogy I'll give you now does fall short in some areas, but essentially you can think of it as if I gave you a box of Lego. You've got red bricks, you've got green bricks, you've got blue, and so on. And each of those different colored bricks represents a different logical or electronic feature. It could be as primitive as an AND gate or an OR gate, could be a little bit more complicated, such as a DSP block doing multiply and accumulates, for example. And depending on how you stitch those together will depend on what you're actually going to get processed in the actual chip itself. In the same way, you could take the same Lego blocks and build a house now, or a castle, or a truck. It's the same blocks, a different construct. You're getting a different output, but that's essentially what we do. So we configure internally in these chips, electronically that is. There's no physical wires changing. You have got a configurable network mesh, and you have got configurable logic, and we cherry pick what we want to do, and that is how these chips actually do what we want. So they're highly configurable and very advantageous for the type of processing that we want to do. Now, the question is why? Why do we actually use FPGAs? There are why not just use a normal CPU? And that goes down to simple architecture. And CPUs are very good at certain particular functions, particularly sequential-based things. Yes, there are multi-core processors. So that analogy does fall away slightly. The difference with FPGAs is because they're so custom, and you've got this fabric that you can play with, they're exceptionally good at high bandwidth processing. And that's why they have been the flavor of the month in radio astronomy for a long time. Omar, I think, referred to the Roach boards being a few hundred out in the wild at the moment. That is absolutely true. In our particular case, Cat 7 was built with Roach, and then initial stages of Meerkat was built with Roach 2. And then we moved over onto Scarab. But the point is that you can do multiple things in parallel, assuming you've designed it like this. You can do multiple things in parallel at lower clock rates than what you could on, for example, an equivalent CPU. So they're really, really good at those sort of tasks. Omar now did also introduce some of these boards for us. There are other FPGA boards that are used in the radio astronomy field. We've only really looked at Roach 1, 2s, and now currently Scarabs. On site, there's 288 of these pizza box looking boards. Each one contains its own FPGA, and each one gets configured. And depending on the instrument that's being built, will depend on how many are being used and how they are being configured, whether it's an F engine or an X engine. And that all happens automatically behind the scenes. FPGAs, while they are still good and have certainly got their own niche market and niche area where they are used, there is a new sheriff in town. I'm going to hand over to James to talk about that new sheriff. He's the head commissioner here for the GPUs, and that is something else that's getting traction now in the radio astronomy field.
Okay, so the background to that is the Meerkat extension project. If you add 20 odd extra antennas, then up to 20 extra antennas, you need to plug them in somewhere. And Meerkat's correlator that we have talked about up to now was kind of already at its limits. We had expanded it once already. It was designed to do that, but it was as far as we could push that particular architecture. And And the Scarab platform that Andrew mentioned is, it started off life in 2017, so it's now a few years old. Anyone who's still using a computer from 2017, well done. It's unusual. So I think the Scarabs have done well. So we did probably about a year's worth of exploration to see, look, what is the next, what are we going to do next for to build a bigger correlator? And ultimately we settled on using consumer GPUs. A GPU is a graphics processing unit. And this is a vastly oversimplified explanation of what it is. GPUs started off life back in the 80s as specialized circuitry in video game arcades for making graphics on, Street Fighter or Tekken or, Amish is nodding. He remembers the corner cafe on those hot summer afternoons. So this is what they were doing, and the profit motive there was, build better GPUs, build better graphics, so you can sell more games. After a while, some people realized that these GPUs, the particular architecture of them, so they had, their task is one thing, so calculations in order to render a matrix of numbers, which is then translated by some decoding logic to the colors that you see on a screen. Like I said, after a while, some clever people figured out that you could use these same kinds of circuits to do number crunching. And because they used to handling large blocks of numbers, they could do it very quickly and very efficiently. So things like big data, machine learning, AI have become industry drivers, and there's big money in that. So lots of research and development towards making bigger, faster, better GPUs. This wasn't always true. And in fact, it's only been true for the last sort of 2 or 3 years that we've had GPUs and the surrounding infrastructure that's capable of handling the bandwidths that we need for radio astronomy DSP, but now they are. So we're at the point now where for about 15 or 20,000 Rand, you can go to the shops and walk out with a device that is capable of doing the work of between 4 and 8 scarabs, depending on how you configure them. I may have oversimplified things ever so slightly there, because you do need to plug your GPU into something. Once you have all these other bits, the cost does go up a little bit. So to give you an idea, but I mean, it's still pretty good going. To give you an idea, one of these server boxes, fully configured, costs about 100,000 Rand. It's doing the work of 4 to 8 scarabs. So I think we win. The scarabs were very, very expensive just because of those FPGAs that were in them. Sorry, I've had a brain freeze and my notes are not here. Any questions on that so far? No, it's okay.
Hi there. I'd like to know, my name is Virushan. I'm from Optimum Solutions in Joburg. I'd just like to know, how long does it typically take to write code that's optimally programmed for GPU deployment?
How long is a piece of string?
Could be anything, right?
Yeah, exactly. So, I mean, you're asking a hard question there. You need to. There's a truism that software is never complete; it's just abandoned. So, if we wanted to, we could carry on tweaking this to the nth degree. But I think the most of the gains that we've had are there. You kind of have to do a trade-off between how much time you have to develop and what your requirements are. We have well, I can answer the question in more detail if you're interested. But to give you an idea, we've got a correlator at the moment, and it's taken us about sort of 2 years of development with three engineers. Versus the Scarab one, which took a lot longer with a lot more people. Yes. 5 years with about 7 people. So the turnaround time is a lot quicker. and there are reasons for that. You know, GPU programming is a lot more mature, a lot more well supported. It's a lot less niche than doing things on FPGAs.
Sure.
Did that answer your question, Rushan? Is there?
Yes, no, it does. Thank you for that.
So yeah, it just depends. Some problems are easier to solve than others, so they happen quickly. Some take a little bit longer.
Sure.
Yeah, there was a question back there. Okay, so just for the benefit of those online, the question is a GPU similar to an FPGA or a CPU? The answer is yes. So FPGAs have and how they work really under the hood is very proprietary secrets of Intel and AMD. But essentially, no, they have programmable logic. So there's you can program the logic to be to do whatever hardware function that you want it to do, and they have these sort of stripes are representing connections. So if you want to have an adder and then a shift register and what have you, you need to connect them up somehow. So FPGAs can essentially do whatever you want them to do. You could have a soft core CPU and program that into the logic, or you can have more a GPU kind of thing. What's typically done is a mixture of parallelism and pipelining. So they can work on multiple things at once, but also you chop your work up into sort of various stages. And the slide that Andrew showed over here is an example of that. So while one bit of data is being we unpack some data from the network, and then we do some synchronization, then we do some delaying. And while that's happening, the next sort of thing is busy occupying the previous stage in a pipeline. On a GPU, on the other hand, it tends to work more in batches. So if I have to make a different analogy, an FPGA is a bit more like an escalator, and a GPU is like an elevator. I'm seeing like nods from a, so I think it started to click. So both of them are for moving people from one floor to the next, but one of them does it in a sort of a streamlined pipeline fashion. The other one, the GPU, you've got to pack people in, and it takes a while to pack them in, but once it's full, you can actually move a lot of people to the next floor very quickly. And that's essentially what we're doing with these GPUs, is that because RAM is so cheap, so that's a difference between, in FPGA land, memory is very, very expensive. There's not a lot of it, so you got to be very conservative about how you use it. On the other hand, and if you're in a server with 64 gigs of RAM, you can buffer up a lot of data, transfer that to the GPU, and the GPU can work its magic on a lot of data in parallel very quickly. So it seems like it's real time, but it's really processing batches just very, very quickly. Make sense? Okay.
There's a question in the chat, but
Okay.
it might be a tongue-in-cheek statement rather than a question. It's does that make the CPU a staircase?
Yes, but a staircase with Usain Bolt running up and down. Although I don't know if he'd like staircases very much. Anyway, yeah, so that's what our correlator in the KDRA looks like. It's currently not powered up. So the computers are there. We're just waiting for networking at the moment. It's going to look like that. That's not a photo of the actual thing. That's just NVIDIA's marketing materials. But they've been ordered and they're on the way. So watch this space. Yeah. Okay. I think that's me. Ty, do you want to?
Okay. Thank you, James and Andrew. Yeah, I just want to quickly go back to that comment about how long does it take to write code. It also does come down to cost as well. So James mentioned the GPU that we're using for Meerkat extension. I think we paid about 12,000 actually for them. Initially, when we wrote the F engine code, we were running it on a GPU that cost about 40,000 Rand. So it took us a few months of, optimization to actually get it down to that. So if we were happy to spend more money on the correlator, it would have taken us a lot fewer months. So yeah, because we are cost bound, as most of you know, we spend a lot more time developing things. But yeah, that's it for the correlator. Does anyone have any questions? Because now we're going to jump over to the other part of the processing pipeline. So it's going to be a whole new world once we cross this threshold. Are there any questions in the chat? Let's see. Okay, cool. Well, then thanks again to James and Andrew. And next up, we have Kim from the pipelines team who's going to walk you through making images, among other things.
Yeah, so as we've already heard all about the correlator part, and the correlator spits out these magic things called visibilities, and those appear in the pipelines team, and then we work our magic on them, as been alluded to. Oh, okay. Oh, will that work? Okay, cool. Yeah, so the reason that radio interferometry works is because there's this very convenient relationship between the visibilities that the correlator has just conveniently spat out for us and this picture of the sky. And it's this relationship here. You don't really have to know that much about it, but if you're technically minded, you'll recognize it as a Fourier transform. So if you just plotted your visibility straight from the correlator, what you would see would be very unintuitive and you wouldn't really know what to do with it. So what we want really is images, because that's something that we understand. And that is basically what SDP is trying to do effectively. And I'll try and explain in more detail how we achieve that. So these are your visibilities, and this is what the sky looks like, in case you've never seen a radio image before, but I'm sure you probably have. Yeah, so the SDP pipeline has these kind of four main systems. The first part is SDP ingest. So all the very high time resolution data from the correlator arrives here, like a whole deluge of it. And SDP's job is just to ingest that, the ingest, and to turn it into something that is averaged down to a slightly more manageable rate so that we can process it more easily in all of our downstream processes. So just to give you an idea, when the visibility data is has like half a hertz frequency, which is about 4 seconds, actually typically we average it down from the half seconds in the correlator to 8 seconds. Then an 8-hour observation is about 40 terabytes of data. So we're processing large volumes of data, and we need to try to slim that down as much as possible. After ingest, the very next process we have is the calibration pipeline, which does what it says. It calibrates the data, and we'll give you more detail on that. And that produces calibration tables and also flags. And our calibration tables get put in this kind of custom metadata store called the telescope state. So between these processes, these arrows are meant to suggest that it's really only data, so only visibilities and flags that flow between here. And all of our metadata is stored in this telescope state and then can be accessed by any one of these processing steps. Once you've calibrated the data, then we can move on to the next step, which is imaging. And there are two flavors of imaging. There's continuum imaging. So continuum imaging really is when you try to image emission that is present at all wavelengths. So when you look at like a light bulb, what you see with your eye is continuum emission, right? There's emission at all wavelengths. And if you're an optical astronomer, you call this photometry. And if you're a radio astronomer, you call it continuum. And you make one image that integrates or adds together all of the emission in all the wavelengths. So you get visibilities in and you get one image out. Once you're done with that step, then we move on to the spectral imager. So spectral imaging is when you only have emission in very distinct, discrete regions of frequency or wavelength space. So you only have emission in a very small part of your bandwidth, and you make multiple images for every single frequency space that you sample. So for the 32,000 channels, you have 32,000 images, which means that you've got 7,000 pixels by 7,000 pixels by 32,000 channels, that you end up with roughly a 12 terabyte image. So it's also, you know, very process intensive. Okay. Do you have any questions at this point? Yes.
That's terrible. Don't record what I'm saying. Hello, sorry, engineer here. It always breaks down at this point here. I'm very confused at that visibilities. When they discuss the visibilities and going into the imaging, what you just explained. Could you go back a slide and just explain that again, please?
Sure.
So I understand that the visibilities come out from the correlator, and are those just like individual values, like
Yeah, the individual voltages from each antenna have been multiplied together,
yeah.
and it's just going to dump out one complex number for every channel that you've sampled, which is that multiplication or correlation.
At the output of the correlator, right?
Yes, yes.
Okay, so that's just an like a intensity value, or not intensity, just a voltage value.
Yeah.
Okay.
Effectively.
Okay, there's complex. Yeah.
So you ignore quantum aspects of it. You just look at the visible light, you feel how long it impacted. And this is just very low frequency way of time measuring. So it's got a, as been said, it's got a Fourier relationship between the phase between the signals and what is actually happening in the phase. Oh, sorry. Yeah. Sorry. Yeah. There's if you've ever tried the double slit experiment, but not from a quantum physics perspective, shine light between two slits and you'll see a sort of a wave interference pattern. You can think of a pair, a baseline, as just like two slits measuring the sort of the radio light, and you can that gives you insight into what is happening in the, is it in parallel or perpendicular? Anyway, in one sort of dimension. And that's one of the reasons that we try and cover, have lots of different baselines so that you can sample this space in many different ways. So Kim will have some more slides about that soon.
Is that, are you happy?
So and what you're saying is that between that that complex number that comes out of the correlator, there's some Fourier relationship to the image that you have in the sky.
Yes, exactly.
Okay, cool.
Yeah.
Thank you.
Okay.
I've got another question. This 12 terabyte image sounds very hectic. How long does it take to do like basic processing with it?
So I think that we process it massively in parallel. So we have multiple machines running it, and we try to, I think it's roughly, we try to do it within 2 hours of our,
Wow.
So if it's an 8-hour observation, you want it to be out within 16 hours, all 32,000 channels. That's
Okay.
our sort of requirement.
Within 16 hours.
Yes.
All right, thank you.
So, sorry, before we continue, can the people online hear me clearly?
Yes.
Okay, so we'll use the mic going forward. The last question before that, apparently you didn't hear, is that correct? Does it need to be repeated? Just the
Yes.
question.
Yeah. Like when they were talking, it was too low, so we couldn't hear it. If they would repeat it, that would be great.
Testing 1, 2. Sorry, I can't remember my question now, but it had something to do with the relationship between the visibilities and the sky image. And what I got out of it is that there's some Fourier relationship between the visibilities. The visibility is the output of the correlator, and that's some complex number that comes out of that. Okay, is that okay? Okay, we'll go back. Thank you.
Okay. Yeah, so that is the magic, that equation. But you don't have to understand the details too much. We'll try and kind of keep it light. Okay, so this is Ingest, which was written mostly by Bruce Mary, who's now part of the correlator team, and this takes in the massive deluge of data that's coming out of the correlator and does basically these steps. It converts it from an integer to floating point. It applies flags. We'll discuss flags in more detail, but a flag is just a mask of data that you think is bad, effectively. So it's data that you want to mark as being possibly not useful so that you can throw it away later if you don't want to. It detects RFI, which we're now all familiar with because of Engineering Week. And it does this on the same time resolution as the correlator's dump. So it does it at the original half-second dump rates. And then it creates these averaged in time and frequency streams that then go to the downstream processes for us to use in a less hectic way. And it computes assorted statistics for the signal displays. So if you've ever looked at the signal displays on the CAM GUI or on the Grafana dashboard, that all comes from ingest effectively. And then we move on to the calibration pipeline. So why do you need to calibrate? Yeah, yes.
Sorry, Tim, one question I want to ask. I know, Andrew, you have a floating point representation of the polyphase filter bank. Obviously, at some point, you must convert it to integer again. Is there a reason we don't just send floating point through? Is it obviously, I think, bandwidth would be an issue?
Yeah, so there's a few reasons for that. First of all, bandwidth, egress out of the FPGA, as James alluded, is, it's we're already pushing the upper limit on what we can do on a 40 gig link. Also, memory internally in the FPGA, BRAM or block RAM is a very, a scarce resource. And in some designs, we're really pushing, at sort of 80–90% capacity. Now, somebody might say, well, there's still 10% to use. It's unfortunately not quite as simple as that. When it comes to getting a design on chip, you have to do what's called closing timing, which means you've got to get your design not only to fit in terms of all the available resources, but you've also got to get it to make timing so that for a particular clock frequency you want to run, your signals have got to be able to make it through the chip within a certain time frame. So you've got your you've got limits as to what you can do there. So of course you can't have too much of the stuff spread out all over the chip. We're not going to be able to use it. So you can never get the 100% resource utilization out of the chip anyway. And if we look at the 32K design, you've got a better chance of finding peace in Eastern Europe at the moment than you do having that design making timing. So, it's unfortunately, it's so tight. It is, we don't have the luxury of working with floating point on that chip. If we were to go to newer generation FPGAs, there's a lot more available resources. But as James said, that the SCARA board is 2017 dated. So we used the best we could at the time.
Any more questions on ingest? Sorry.
Thank you. I just want to ask, from the correlator, you have like these dumps at half a second. Is there a reason why we can't but then we average them to 8 seconds? So is there a reason why we can't just have them as like 8-second dumps from the correlator straight? Why do we have to, is there any maybe scientific reason why do you have to have that high dump rate?
So Bruce is listening, so he'll correct me if I'm wrong. The correlator doesn't do any detection of RFI or anything like that. That's the sort of the job of the ingest machine. And the ingest machine does it. Kim, can you go 2 slides back? Okay. It detects RFI by having access to a fairly large portion of the band. And if you have this much data and you see, this sticks up quite a bit over the other stuff, then you can kind of safely say that that's RFI. The X engines have just this little slice that they're calculating. So in principle, we could do it, but then they would need to talk to each other to sort of communicate these kinds of things, which is hard to do in real time. It's an idea that I've got percolating in the back of my mind somewhere, but I haven't thought of a good way to do it yet. But yeah, that's one of the primary reasons that it's not done like that.
Yeah, so if I can add to that, at least the initial idea was that we do this RFI detection at that half-a-second rate, so that if there's some sort of sporadic RFI from electoral shorting or something, we could pick it up before we average it together with good data. It's not entirely clear that that's actually proved to be effective, and I think it might be getting reconsidered for the Meerkat extension.
Thanks, Bruce. That was useful. Okay. Any more questions on ingest? Luckily, Bruce is on the call, so he can actually answer them. Okay, yeah, so we'll move on to calibration now. So why do you have to calibrate? Well, basically, there's just a whole bunch of corrupting effects as your signal is traveling from the source in the sky all the way down to your computer chip. Like, lots of things happen to it. And at the end, the thing that you're actually measuring is actually very different from the visibility that I put in that nice equation at the top. You don't actually have that when you actually start processing. And so if you were to just image what came directly out of the correlator, it would look pretty terrible. You wouldn't really see anything useful. You know, some of these effects are things like the atmosphere. So I think a very relatable thing is if you're standing on the hill at like Lion's Head or something and looking over the city, you can see that the lights of the city twinkle, right? And you know that it's twinkling because of the atmosphere. Like, these little bits of atmosphere are refracting the light, and it's causing that effect that the lights kind of move and they change in their intensity. And so you have a very similar kind of thing in the radio. You can, the atmosphere will cause the phases of your sources to shift and for their positions to shift, and the image will become defocused. But including all these other effects just makes that even more extreme. So the point of calibration is to remove most of those corrupting effects. And we typically do that by modeling them. But some corrupting effects like RFI are harder to model, and they're also relatively confined. So we just flag them and chuck them away rather than going through the work of modeling them. So just what we kind of really do here in the calibration pipeline is we model it and try to measure that modeled effect by using pre-known calibrator sources. So you already know what the visibilities for those calibrator sources should look like. So you have model visibilities because you already know the features of that particular source, and you have measured visibilities, and then you just do a model fit and you work out these calibration solutions, which conveniently can almost always be expressed as antenna-based values. So instead of having n squared calibration solutions, now you only need n, and you can store those in telescope state, which then kind of keeps everything relatively simple. And the goal then is to take visibilities that look like this when they came in to something that looks like this, because this is what you think your calibrator should look like. Yes.
If you just go back a slide, you listed a few interference, so atmospheric effects. How dynamic is that, and how often do you have to update your calibration?
So it depends a lot on your individual wavelength. You know, different wavelengths have different effects. But say for Meerkat, I mean, we typically only have to do atmospheric type calibrations kind of every hour, and we think it's relatively stable. But then that's when you visit a calibrator. But then we'll discuss further on, you can do self-calibration, which allows you to resolve those effects on a higher time resolution. And then you can go down to like 30 seconds if you want to. So you don't have to visit a calibrator every 30 seconds, but you need to take out those effects relatively quickly. Yeah, and so once you've put these things in the telescope state, they end up in our data file, and you can dynamically apply these calibration solutions. So one point about our data is that we don't really change the data once it comes out of ingest. All we do is take the visibilities from the correlator and we average it, and then that is what ends up in the archive. And all of this other processing, like the calibration, is just metadata that you can dynamically use to alter your data as you need it. And you have the option to use it or not use it, or only use part of it as you would like. So that allows kind of a flexible calibration model. After that, so the other thing about the calibration pipeline, sorry, I should have mentioned, is that it's running basically while the observation proceeds. So we buffer up data as it comes in and calibrate it on a sort of chunk by chunk basis. And roughly 10 to 15 minutes after the observation is done, you're done with calibration, and we can start straight away with imaging. And this is a kind of fairly unusual system. Not many other telescopes do it like this. So it's kind of specific to Meerkat. So then we move on to the continuum imaging process. And this process has three kind of important goals. One, it does self-calibration, which is a new step of like a second order calibration on top of the calibration we've already done. It does imaging and deconvolution, so it makes the actual images, and it does continuum subtraction, which you need for the next step, which is the spectral line imaging. So self-calibration, so as we're kind of just discussing about the atmosphere, the problem is when you calibrate on a calibrator that's not exactly in the same part of the sky as your target, the atmosphere is not exactly the same. So you'll never get the best quality image that you can get. And so in the 90s, they invented this self-calibration to get around this problem. So what you do in self-calibration is you make an initial image from your roughly calibrated data that from the previous step. And that's usually good enough that you can kind of see some little sources in there. I don't know how well this image is showing up, but there are little sources. And so you make a model from your rough image, and then you do the same process that we did before. You make your model visibilities, you solve for your calibration terms, and then you just iterate through this process. And eventually it will, if everything goes well, it will converge and you get a reasonably good image effectively. It's kind of magic, but it does work. But because you actually need this image, obviously the step is like inextricably linked with the imaging. You can't actually separate it from the imaging. That's why it's in this part of the process. And then you have to make the actual image. So what goes into imaging? One is this Fourier transforming of the visibilities. And it's a little bit complicated because it's not exactly a Fourier transform. But also you have to compensate for the fact that you have incomplete sampling with your telescopes. So those visibilities are a function of what we call UV space, which is the separation between the antennas. And if you could just blanket the whole Earth with antennas, then you would sample the space perfectly and you would have a great image. But obviously that's not practical. You just have a few antennas. So you only have a smallish sample here. And so because of that, there's some distortion in your image because of this incomplete sampling. And as I'm talking to a bunch of engineers, I don't really think I need to explain this in too much detail, but just for anybody who's maybe not familiar, you can kind of just think of it as like you're on your WhatsApp call and there's some bad connection. And the worse the connection is, the harder it is to hear the person, right? So the more sampling you have, the better the connection, the better the call kind of thing. Yes. Oh, sorry, the mic.
In your previous slide, so you said that you iterate towards a solution.
Yes.
And how do you decide the threshold that something is good enough? Is it a manual or automated thing?
So you can set it like just an auto threshold. I only want to do this so many times if you want to. Normally with something like Meerkat, you just come up with a heuristic, like I think this will work most of the time because it kind of does work. Or you can try to say like, how much is your solution changing? You know, is there a large change in your solution or is it more or less staying the same? And the same, is the image improving? Like, is your noise going down? Is the residual that you're getting smaller? And once that starts to flatline, like there's not much point anymore in continuing. Yeah, so that is what deconvolution is. It's kind of removing the effect of this incomplete sampling. And there's, so the worse your sampling is, this is a image from the VLA. If you only have a very short observation, you'll have very incomplete sampling. But luckily, when the Earth rotates, that vector of the separation is actually going to rotate from the perspective of the source. And so you can fill in this UV plane, and that gives you more and more sampling. So the more sampling you have, the better your image will be. And you can kind of get that for free by just observing for longer. But roughly once you get to 8 hours here, I mean, you can see rotating more isn't going to give you any better sampling. So there is a limit here, but the better you sample, the better it's going to look. But on top of that, we can also improve on that by doing some extra processing to try to remove this effect, this distortion effect. And the way that this kind of works is that, roughly speaking, the distortion is if you have your picture of the sky, then these are little point sources. The distortion is that every single point gets convolved with something called the point spread function, which is the Fourier transform of your UV distribution. So then the image will look like this. Every point will just be surrounded by this point spread function. And we call this the dirty image, when it comes out in its natural form, once you Fourier transformed it, this is how it looks. And when you want to deconvolve, you really just do this process in reverse using an algorithm called clean as the most basic one. There are many other kinds of ways of doing it, but this is what we typically do. You just say, here's a point. I take this point, I subtract out the point spread function, and I put back the point. So you just do this in reverse, and you do it many, many times. And then at the end, you get a better looking image effectively. So that's what we're doing. We're doing the calibration and the imaging, and we do this iteratively until everything converges. And then we store our calibration solutions in TelState, and we also store this model image in TelState. Oops, sorry, I went too far. I went too far in TelState. And so that you can then do the next step, which is the continuum image, the spectral line imaging. Okay, so once the continuum imager is done, then we move on to spectral line. So spectral line, like I said, is really confined to just a few small channels, and continuum tends to be much, much brighter. So if you ever looked at a Meerkat continuum image, you'll just see thousands of sources. The image is very dominated by that. And your spectral line image is going to be much fainter, and it's also going to be present for only a few small channels. So it's very hard for you to see that with all that confusing continuum emission in there. So typically we just subtract it all out to make it easier to detect the thing that you're actually interested in. So this is, you can't really see it that well, but this is a continuum image, and this is an image, a spectral line image of an empty channel. So if you look through these 32,000 images, only a few of them actually have something in, the rest of it's just basically empty. And you'll see then this is a spectral line image where you've got a few channels where there is emission, and the emission changes in every channel. Whereas if you had the channel image like this of the continuum, it would all look the same, right? Every channel would look exactly the same. And so I have here a movie which is stepping through some channels of an actual galaxy detected with the actual SDP pipeline. So yeah, so the contours here outline the overall shape of the galaxy, and you'll see the spectral line coming in and out as it goes. See, there you go. The emission is now starting and it's moving. And then the reason that you have the emission in different channels here is because the emission is emitted at the same, native frequency, because it depends on your atomic processes, but it's in different channels here because there's Doppler motion. So you're actually seeing the movement of these of the gas in this galaxy. And I'm not a spectral line scientist, so it took me a while to make these plots. But this is just another example showing you this is the overall profile of the galaxy. This is what it looks like in one channel. And then you can take a slice in frequency across this, and then you'll see this is the actual emission as a function of frequency for that whole block. And this is just a nicer picture, a nicer version of that. And yeah, any questions about spectral line?
Sorry, just back to the UV space. Does it make any sense to do interpolation to do during the deconvolution process to get some more resolution? Does that make any sense, or does it not really help?
I
After
think
this and the point spread function, the only technique that you apply there.
Yeah, well, we only really use clean. There are multiple methods of trying to get rid of this effect. I think you could call clean like a fancy interpolation, really, but the man in front of you, Ludwig, is more of an expert on these kind of things than me, so I'm sure he can give you some useful tips on that.
Well, yeah, the interpolation sort of happens implicitly through the clean algorithm, but it also extrapolates beyond the dishes. So it's sort of saying you're assuming the sky is full of small point sources, and that means there's sort of the visibilities would have gone on beyond your telescope's reach, and you sort of extrapolate it as well as part of the process.
Okay, then yeah, this is really my last slide. Oh no, I forgot, we're doing flagging. Sorry, I forgot about the flagging. Okay, yeah. So as I said before, a flag just marks faulty data, so it can be excluded from processing as desired. And flags are one of the things that the SDP kind of adds to the whole data mix. And our flags are stored in 8 bits, where every different bit means a different type of flag. So here it's not just whether to exclude it or not, but why you think it's excluded. These are the different types of flags, and I've highlighted in purple the ones that the SDP kind of produces, and it roughly follows the data processing flow along here. So reserved is not used, luckily. And then we have what we call, these are the CAM flags. So CAM flags are really, I think, as Ludwig will say, it's really anything that you know about, that the system knows about, that can tell you that the data is faulty. So things like, is there a sensor that says the antenna is in wind stow? Is there a data suspect sensor? Anything that the system already knows about gets marked as a CAM flag. Data lost is what it sounds like. Data's gone missing, either typically between the CBF and ingest, if data's gone missing there, but also if you're accessing data from the archive and there's like a flaky link to the archive, it will also mark that as data lost. And we have this dream of predicted RFI, which is currently not used, but you could hopefully one day predict all the satellite RFI, which would be useful, but we just haven't had time to implement that yet. So then the main flags that we already have is we have a static mask. So the static mask masks the edges where the filter roll off is, because we don't really want to use that for science. That's masked all the time. And then we also mask very badly RFI polluted regions, and we only mask those on less than 1 kilometer baselines. And we basically mask those because our RFI detection algorithms are just not very good at doing this very well. So we just say it's bad all the time and we throw it out. And we don't really want to keep this data because it tends to really corrupt our calibration solutions, which then get fed back into your data, and it just becomes kind of self-reinforcing. Then we have the ingest RFI, which, as Bruce said, was this idea that you would detect RFI at a very high time resolution. But because we have very high data volumes there and we really need to process things very quickly, it's kind of a more basic level RFI flagger, where it just does a median absolute deviation filter, and it only throws away the really worst case RFI, and it only detects it in one dimension across frequencies, basically. And this is the RFI that you see displayed on the signal displays, because obviously the signal displays come from ingest. Then we have the calibration RFI detection. So here it's detected at the longer 8-second dump time, so not such high time resolution. And it has a slightly, it's less conservative. It tries to flag as much as possible. And it basically detects these, amplitude spikes across the frequency space, but it detects both in time and frequency space, and it has a slightly more signal processing type approach to getting rid of this RFI. And then we also have something called a post-processing flag, which is a flag that gets applied if something has gone wrong with our calibration, and it's basically applied by CatDel if you open the file and try to apply calibration and it finds that there's a problem with our calibration solutions, for example. So that's flagging. And so in the end, you have all these products in the archive, which are built on top of the products built by the correlator. And most of these things are things that are produced by SDP. So you have the data file here, which includes the data, which is the data from ingest, plus the metadata, which was added to by all these other processes. And you have the images from both the spectral and continuum line imager, and this little report here that tells you how the calibration went, and a few other reports. So any of these things can be accessed by ourselves for internal quality assurance, or by scientists who want to use it to do science. Thanks very much.
Thank you very much, Kim. I just want to check if there's any more questions for Kim specifically.
There's a hand online.
There's a hand. Bruce?
So you very briefly mentioned signal displays, but you didn't really talk about them. And I know Matthew's not part of the team in DSP anymore. Is signal display still something that DSP is responsible for?
I'll get back to you on that, Bruce.
Awkward questions.
Sorry, Bruce.
You love this guy. Yeah.
Yeah, that, I mean, on a more serious note, that is something that we still need to properly figure out with the whole splitting of SDP. There's a lot of things we still need to figure out. So yeah, we'll get back to everyone who's interested in that soon. Roford, I think, had a hand up.
Do you use any special hardware for all this processing?
Yeah, I'm really not a hardware person, so I'm not very good at answering that. I mean, for the calibration, we have nodes with very high amounts of RAM because we buffer up all of those incoming visibilities. So those are sort of, I guess, custom amounts of RAM that we've specified. But otherwise, the rest of it is just like normal, servers with GPUs and CPUs. It's not like a FPGA or special purpose built things.
Thank you very much. I want to know, so we store all this data that comes in from the UV data, in an image that's 12 terabytes, and it's stored as well. But you were mentioning that all this data we've got, there's data that's also, there's nothing in it. So I want to know, when do we actually describe the data? Or do we just keep it and for research later on?
Yeah, so the model that we have at the moment is that the data stays on the, in the live spinning disk archive for 200 days. I was informed. I thought it was 6 months, but apparently it's slightly longer. And then it gets put onto tape and it lives in tape forever. We never delete it. So yeah, we were basically keeping this stuff forever for potential use in the future. The only tricky thing is that it's actually very difficult to get the images back off tape. That's still, like to be TBA, whatever.
Okay. Thank you.
Okay, thank you very much, Kim. I see there is a note from Sarah in the chat that Matthew will be talking about signal displays tomorrow. So I think signal displays have just followed Matthew.
Yes.
And I believe in the SE group at the moment. Okay. Whoops, not Zoom. Okay, this brings us to the final part. Oh, there's a question? Sorry, go ahead.
Does it make any sense to compress any of those data, or is it not really suitable to compression, or takes long, or not really worth it?
Yeah, I don't really know much about that, so I can't really comment. I think it is possible, but it hasn't really been looked into, and we didn't plan to compress them at the start. So yeah.
And I can add that, I mean, it's Gaussian data, so it has a bit of compressibility, but it's like pretty noisy, like we're making, our signal is noise and the noise is noise. So if you look at the data, it's basically staring at the snow on a TV screen for like 10 centuries. That's basically it.
Yeah, I think there was also a response in the comments. I'm not sure if you can see it here, so I'll just read it out. It also says, it depends how well the data is calibrated on how much you can compress.
Okay, all right. We're now in the final part of our presentation. So thank you for sticking around this far. We're probably going to be a minute or two over time, so please just bear with us. Thanks for all the questions. Last but not least, we also just want to talk a little bit about research and development that our group has started doing. So obviously we've built the Meerkat correlator and the Meerkat pipeline, and we're building the Meerkat extension correlator and pipeline. And when we built the new correlator for Meerkat extension, it was kind of a bit of R&D because we've moved from FPGA-based correlators to GPU-based. And a lot of, as we sort of wrap up Meerkat extension development, a lot of our team is actually moving into this blue sky research R&D phase to figure out how do we build the next generation of correlators and pipelines for radio astronomy. So Andrew Martins is going to talk a little bit about one of the projects that we've started up this year for R&D. Thank you, Andrew.
Cool, thanks, Ty. I'll try not to be too long. So yeah, as Ty said, we sort of know how to build correlators. We've been doing it for a while. And I guess our team is looking at building better and better ones. So like looking into the future, there's going to be like higher and higher bandwidths. And obviously we're going to try to solve some of the issues. I know when we were thinking about Meerkat originally, there was this idea that we'd be continuously processing data, and we kind of haven't quite got there yet. We kind of store it and then process it. We haven't got the full pipeline thing going, but hopefully in the next few years, we actually we'll get close to that. So there's some R&D looking at algorithms and things like that. Andrew and them are doing. And then one of the things we're looking at is also hardware that might help us with this thing. So the thing we're looking at is something called a smart NIC. So a traditional NIC there on the left, data coming into your PC or whatever would use one of these. So the data would come in, typically it would get stored in, depending on the drive or whatever, it would get stored in a bit of your system memory, and interrupt would then ask the processor to come and look at this data. The processor would come, decide what to do with the packet, probably copy it out into another part of memory, and then eventually your application would sort of get this data. The problem with that is that it uses the CPU a lot. It uses quite a lot of memory sort of accesses. And when you're streaming huge amounts of data different types of data, like your CPU just can't keep up. So recently they started looking at improving NICs to allow basically more data to come in and out of your processor. And they've got these thing called smart NICs, and there's different levels of smart. So there's things that allow network offloading. So basically the idea is that you're moving some of those tasks away from the processor and into the actual NIC itself. So it takes away some of that work that the NIC's doing, and maybe some of the memory accesses too. So stuff like responding to ping packets, say, like the processor doesn't have to go and look at a ping packet and decide it's a ping packet and then respond. You could have the NIC do that just by itself. There's also stuff called, there's stuff being done around DMA. So basically the idea is you can copy the data directly from your NIC into memory instead of having going via the kernel and via the operating system. There's something called remote DMA. There's sort of various protocols and stuff being developed and tried out that allow you to almost, from your source PC, send it directly to a location in the remote sort of processor sort of space. And then the thing that I call the super part of it is we're going to look at actually possibly implementing astronomical algorithms in the smart NIC. We're going to evaluate whether it makes sense to actually do astronomy things in the FPGA. So on the right here is one of these smart NICs developed by AMD. And this one particularly has an ARM processor with 16 cores on it, and that allows you to do a lot of network offloading. So it can do even custom stuff. You can write code that'll run on there that'll look at your packets format, say your custom packet format, and do things with the packet for you. So what we're going to be doing is we're going to do some research to find out whether it makes sense to use these things just in theory. Are there parts of the pipeline which make sense to actually do, say, in an FPGA, do this sort of super part of it, and look at different types of commercial off-the-shelf NICs. There are smart NICs that, like that previous one, that you can sort of buy and just configure. And then in parallel, we're actually going to be developing some prototypes with some hardware we've already got. We've got these Alveo boards. And the idea is that we can hopefully take one of these Alveo boards, find a nice platform. These development platforms are out there for smart NICs, and then hopefully add our own custom DSP and produce something useful. That's what we're hoping. And that project we're hoping to be done sort of beginning of next year, have these some of these prototypes, and have sort of hopefully had a first stab at deciding whether smart NICs are something we want to be using as part of our sort of data processing pipeline. Cool. Any questions? Cool.
Cool. Thank you very much, Andrew. All right, and that is it for the digital signal processing group. Are there any other questions? We would show you the lab, but there's nothing very exciting besides a few flashing lights. So if you want to see flashing lights, let us know. We can take you to our lab. But most of you have probably already been there. And yeah, otherwise, thank you very much for your time and thank you for all the questions.